All right. Remember our crazy saying pKa phosphorylase, phosphorylase kinase, phosphorylase kinase, phosphorylase glycogen phosphorylase, which phosphorylizes glycogen to remedy a low blood sugar level, right? So we've learned about pKa and we've learned about phosphorylase in terms of their structures and how they function. Make sure to go back and look at those videos for the story of pKa and how it works, and the story of phosphorylase and how it works, if those are not familiar, because I'm going to be using those to help us explain this one last piece, how phosphorylase kinase works. Okay, so before we do that, I'm going to very quickly go through and look at the catalytic structure. I've got it down here at the bottom of pKa and remind us of how that works. So this is the pKa catalytic subunit. And remember, we want to think about R2C2 when we think about pKa. So we've got 4 subunits that are part of pKa, specifically when it's in its inactive state. We've got 2 catalytic subunits and 2 regulatory subunits. And what happens when this enzyme is inactive is those regulatory subunits act as competitive inhibitors binding to the active site. They have that inhibitory domain that binds in the substrate binding site of the catalytic subunits, and you've got this 4-part assembly that essentially prevents it from doing its phosphorylation chemistry. Well, how did we remedy that? Remember, we had cyclic AMP. Cyclic AMP is a need state signal, so it's going to be activating pKa, which is a phosphorylator. So what happens is cyclic AMP distracts those regulatory subunits. Those regulatory subunits bind to cyclic AMP, and that allows for the dissociation, the freeing of those 2 catalytic subunits. Okay, so that's how we think about pKa and its activity. So I want to take a second and look in the enzyme active site of the catalytic subunit, because we're going to see a lot of similarities with what we see in the catalytic subunit of phosphorylase kinase. Okay. So catalytic subunit here we can see in orange, we've got our substrate that we're binding that's going to be phosphorylated. So at this white position, let me zoom in even closer here. At this white position on our substrate, that's either a serine or a threonine that's going to be phosphorylated. We've got a recognition domain with different, and we didn't even need to know what those were in pKa, but there's certain residues that will be flanking that serine or threonine, specifically indicating that it is a substrate for pKa to phosphorylate that serine or threonine. We can see that the phosphorylation comes from ATP. So this is ATP that's here. The terminal or gamma phosphate is going to be transferred onto that position. And critically, we've got threonine 197 in our catalytic subunit. That threonine itself is phosphorylated, and so we're going to be able to have a negative charge there that's going to help bind to, orient, and stabilize the binding of our substrate. So that's how pKa's catalytic subunit works. So we're going to look at a lot of homology with what we're going to see with the catalytic subunit of phosphorylase kinase. So here, up top here, is the catalytic subunit of phosphorylase kinase. But before we get to that, I want to look at not the R2C2 story. This is an alpha, beta, gamma, delta story. And we've got this story up top here. So we're going to go through this to explain how phosphorylase kinase becomes active. It is also a tetrameric enzyme, okay? We've got 2 regulatory subunits, but we call them alpha and beta. We don't have 2 catalytic subunits. We have 1 catalytic subunit, and we call it gamma. And then we've got 1 other subunit, which we call delta. So these 4 pieces come together, and that makes, in this case, it's going to be an inactive catalytic subunit for phosphorylase kinase. Okay, so what we're going to have here is these 4 subunits when they are together, okay, and we do not have the alpha and the beta subunits phosphorylated, and we do not have calcium binding to the delta subunit. We are in a conformation where the gamma subunit auto-inhibits itself. Do you remember we talked about like a competitive inhibitor for the catalytic subunit of pKa? The regulatory subunit put something in the mouth of the catalytic subunit, okay? What happens here is this gamma subunit inhibits itself. So it's almost like if you can imagine if I was a catalytic subunit, I would be in a shape where I put an inhibitor in my mouth. If my mouth is the enzyme active site, I would inhibit myself. So how do I then become active? I have to change my shape that moves that inhibitor domain out of my active site. Okay, so how does that happen? Remember, we've got our phosphorylase kinase as a tetramer. We're going to have the alpha and the beta subunits when it's inactive being not phosphorylated. We have a shape in our gamma subunit such that it is binding its own inhibitory domain, and then the delta subunit is not binding calcium. So what happens to kind of shift it so that our gamma subunit is active? Now, unlike pKa, we don't have a physical separation here, but what happens is these two regulatory subunits, alpha and beta, get phosphorylated. So that's what we're showing here. So they get phosphorylated. Our delta subunit binds calcium. Those three events, phosphorylation, binding calcium, change the shape of this. They all stay together, but it changes the shape such that our gamma subunit pulls out its self-inhibitory domain and now can bind substrate and do phosphorylation chemistry. Okay, so that's that big picture. So highlighting what we see here in the enzyme active site. Again, just highlight, this is what we already talked about. We've got two regulatory subunits, alpha and beta. Okay, they become active when they're phosphorylated. Our catalytic subunit, we're going to look at the structure of it just in a second. And then we've got this, I don't have the delta subunit written on here, but that's sort of this fourth subunit here. But let's talk about the catalytic subunit, okay? So we're going to zoom into the enzyme active site here. We're going to see a lot of similarities to things that we saw with the catalytic subunit for pKa. Okay, they only show a tiny little piece of the substrate here, but there's that orange substrate again. We're going to have that white domain representing a serine or a threonine that is going to be phosphorylated by this catalytic subunit. We see ATP that's bound here. Here's a phosphate that's going to be transferred to that serine or threonine. So lots looks the same to what we saw here with pKa. One critical difference. This threonine 197 that we saw in pKa's catalytic subunit that gets phosphorylated is replaced by a glutamic acid residue that we have here in our phosphorylase kinase. So let me highlight that here. Okay, this glutamic acid residue here. Now, why this is key here is this mimics a phosphorylated threonine residue. So it looks like it's threonine 197, but always phosphorylated, okay? Remember that for pKa's catalytic subunit to be active, we had to have that threonine 197 be phosphorylated so it could properly position the substrate. What we have here with phosphorylase kinase is we've got a phosphomimic that's in there. It is a residue that mimics a phosphorylated threonine residue. So it's always active. So looking back at the words that we have over here, we've got that threonine 197 that's replaced by a glutamic acid. So that makes this enzyme what we call constitutively on. It's a fancy word for just saying always on. And we highlighted too, it's not shown here in this picture, but we have inhibition of that catalytic subunit by an intramolecular C-terminal domain. Okay, so there's a part on this protein. It actually doesn't show it over here, but this can normally come in and it can inhibit its own active site. How does it relieve that inhibition? When you have the regulatory subunits get phosphorylated and the delta subunit bind calcium, there's a conformational change that pulls that inhibitory segment out of its own mouth, out of its active site, and it can phosphorylate its bound substrate. Okay, so now we know all the pieces for our phosphorylation cascade. Just highlighting, again, some big picture things. pKa phosphorylates phosphorylase kinase. pKa is the R2C2. We've got catalytic subunits that dissociate from the regulatory subunits in the presence of cyclic AMP. Phosphorylase kinase phosphorylates phosphorylase. Phosphorylase kinase is a tetrameric protein, has one catalytic subunit that when we phosphorylate the alpha and the beta regulatory subunits, hint, they're phosphorylated by pKa, and we bind calcium, we are able to then phosphorylate phosphorylase. Phosphorylase phosphorylases glycogen. Phosphorylase is that enzyme that has that N terminus that's either buried or exposed, and we've got a serine 14 residue that's critical for whether or not we're able to bury that residue. Hint, that serine 14 is phosphorylated by phosphorylase kinase. So we know all of these details now for how we can put these pieces together to ultimately take a signal, low blood sugar, and remedy it, break down glycogen into free glucose. Wow, I know that's a lot, but hopefully these videos help you sort of put these pieces together.